Welcome to another session of multivariable calculus class. Today we are going to deal about triple integrals. So as you are remembering, you are taken double integral over a rectangle. So here we are taking triple integral over a rectangular box. Just as the mass of a piece of straight line y of linear mass density delta x, where a less than or equal to x less than or equal to b is given in a single integral, right? This we have seen as a single integral. Now when you have moving to double integral, it will be double integral over d sigma xy dA rho xyz is a triple integrals. Now in triple integrals we should consider, instead of a rectangle we should consider a cube like this. Previously it was rectangle, so now we are having a block like this. Now it is from its length is from A to B, its length, then it's of C, y is varying between C and D, so this is C and D, and this entire length, another thing will come now, that is between P and Q. So like that we will have three partitions like this, that is from AB, interval AB, this is partition for AB, this is partition for CD, and this is partition for PQ. So we are having x naught less than x1 less than xn, xi minus 1 less than xi less than x. L is the, so last point is L, xl. So xl equal to b. Similarly, the interval CD is partitioned into y0, y1, y2, etc. Ym, and PQ as z0, z1, z2, etc. Zn. Now this each of with a length. First one is delta x equal to b minus a by delta x equal to b minus a by L, and delta y is equal to, what should be, d minus c by m, and delta z, it is of the type q minus p by n, right? Now these are going to be your intervals. This we will say that LMN boxes altogether it should be LMN boxes. Okay, so n equal to LMN boxes B111, B112, BIJK, BLMN, last one. Now each of this is of volume. Delta V is equal to delta x delta y into delta z, delta x delta y into delta z. Now when you are moving in a double integration itself, we are taking a point of evaluation. That point of evaluation is xij, xijk, yijk star, and zijk star be an arbitrary point in Bijk if L, M and N are large, so the dimension of Bij are small. What it says is that taking this point, we will calculate what is rho of xij star, yijk star and zijk star. Now we will calculate its mass is equal to the density is equal to mass by volume, right? So you can have mass is equal to density into volume. So here we are having rho of xyj ijk star, yijk star, zijk star into delta V. Delta V is the volume of that small box. So here delta V is equal to delta x delta y into delta z. Now adding up these masses together, we will get the mass of the n boxes. N means M, N and L. LMN, right? So LMN boxes. So we can, in order to get this mass of entire object, we should add up these all masses together. So it will result sigma over I equal to 1 to L, sigma j equal to 1 to M, sigma k equal to 1 to N, rho of x I j k star, y I j k star, z I j k star into delta V. Now this summation will be with this an approximation, right? To get a better approximation, what we have to do is this L, M and N should be very large. That means whenever limit L, M, N tends to infinity, this summation is called the Riemann sum. So equation 1 is an example of a Riemann sum. So this is the Riemann sum. Now as this LMN tends to infinity, this will become triple integral. Each sum will become the integral of, this will become rho of sum xyz into dx dy dz. So this will become, this is integral with respect to x, with respect to y and with respect to z. So this is the definition of your triple integrals. So definition: triple integral of f over a rectangular box B, if f is a continuous function of three variables defined on a rectangular box B, and let P equal to Bijk be a partition of B, a Riemann sum of f over B with respect to the partition B, P is a sum of the form sigma I equal to 1 to L, sigma j equal to 1 to M, sigma k equal to 1 to N, f of x I j k star, y I j k star, z I j k star into delta V, where this is a point in your considered rectangles, right? Now this will become the triple integral over f as triple integral over B f of xyz dv equal to limiting value of L, M, N tends to infinity, sigma that enter sum. So this is the definition of triple integral. So definition is same as your double integral. Only difference is that one more summation is coming, and instead of a rectangle, here we are taking a box. So let us see one example also. Before that, that's a theorem. Let f be continuous on a rectangular box, right? B equal to x, y, z, x lying between A and B, y lying between C and D, and z lying between P and Q. Then the triple integral over this box B f of xyz dv is equal to triple integrals. See, first of all, f of xyz dx dy dz. So when I'm starting with the dx, so I should write the limit of x here, right? So x is lying between a and b, that limit. Then next is dy. So the dy limit should be here. Next is dz. So the last limit should be, or the first limit should be with respect to z. I think you can follow this order, right? So let us see one example here. Evaluate triple integral over b. So triple integral over b is given is x square y plus yz square dv. So what we have to do? Separate. Each interval is given. So it is dv. So we should write it as integral over, instead of first I am writing in terms of x, so it is from -1 to 1, first limit. Second limit is from 0 to 3 with respect to y, and next is from 1 to 2. 1 to 2 I should find x square y plus yz square into dx dy dz. So it is easy to calculate, right? So here the problem has been worked out here. So first we are finding the derivative, the integral with respect to x, treating y as and z as constants. So with respect to x, when you are finding the integral, it will become x cubed by 3 into y, right? So x cubed by 3 into y, this term, and next term doesn't contain an x, so it will become yz square into x, right? Now between the limit -1 to 1, apply the limit, you will get the expression in y and z. Again, this integration is with respect to y, so integrate with respect to y, this will become y square by 2, 2 get cancelled, you will get y square by 3. Next thing, here is 1 y is there, so y square by 2, 2 will get cancelled, you will get y square z square. Between the limit y equal to 0 to y equal to 3. And next we want to integrate with respect to z. Now this will become a function of z alone. So when you are finding the integral with respect to z and apply the limit, you will get the answer. I think you can follow it very easily. So I'm moving to the next one. Triple integrals over general bounded regions in space. So we have come across the same case when you are dealing with double integral also. So we have converted the surfaces into rectangles, and in general cases we cannot have such perfect rectangles. So what we are going to do is we'll define another function, right? So there we have defined some f of xy such that if it is having intersection with this equal to f of xy itself if your xy is lying in the rectangle R, right? Or else 0. This was the case in your double integrals, right? Double integral case. So here we are having triple integral. So here also you can define the same way the function. So here's the way. See it. F of xyz equal to f of xyz if xyz is in t. What is t here? See in the picture t is given, 3. See, this is your t. That means the required region or the required solid, right? If it is having your xyz is in here, means you are finding is f of xyz, otherwise it is 0. So here is given. Suppose T is a bounded solid region in space, right? So we have first of all defined like that. Now we can go for the Riemann sum over this T. So Riemann sum over this T you are finding. Now when your L, M, N tends to infinity, you will get the triple integral. So this is defined for a general solid, right? Or a general we can say that a bounded solid region. So here we have to note two things. That is, f is continuous, then t is sufficiently smooth. It can be shown that f is integrable over t. And second thing is that properties of double integrals is easily applied for the triple integral also with a suitable changes. Now evaluating triple integral over general regions. So general region means we are having previously you are having x symbol in y symbol, right? These two we have defined in your double integration classes. So here x symbol means it should be a function of y, right? Then y symbol means it should be a function of x. Here we are having a z symbol also. So here what's the difference is that x should be a function of y and z. Then we will say that it is x symbol. So x symbol means it should be a function of y and z. So what should be y symbol? It's a function of x and z. Then z symbol means it should be a function of x and y. So this is the difference here. And we have done double integration in x symbol cases, y symbol cases also. So here also we can do in triple integration x symbol, y symbol and z symbol regions. So here is given one example. See, k1 x1 less than or equal to z less than or equal to k2 xy. So this is z symbol, right? So this is a z symbol one, where r is the projection of t onto the xy plane. So what is here? T. So this is your t. This projection is coming like this. See, this r. Then what we have to do is we have to find the triple integral over this solid region f of xyz dv. So that will become integral over c z. Its range is from, first range is from k1 xy to k2 xy. So we can replace the ranges with k1 xy to k2 xy. Now the remaining is same as we are doing in your double integration class. So here again we are considering r. So here y is a it is going to be x symbol, right? When you restricted those to your r, it will become y symbol, sorry, x symbol. So it is y symbol. Then it should be in triple integral over t f of xyz dv is equal to integral a to b. Then integral of y should be function of limit of that should be function of x. So g1x to g2x f of xyz dy is coming. Now as we are doing in your double integration class, we can easily find the limit. Here is one example. Evaluate triple integral over z dv where t is a solid in the first octant bounded by the graph of z equal to 1 minus x square and y equal to x. Okay, so here two graphs are given. T is shown in figure. So this is the figure. So what we have to do is we want to find double integral over z, and the function given is z, right? Z dv. So that's equal to double integral over r. First I am finding what is the limit for z. So z is ranging from where to where? Around this line, right? Z is ranging from here to here. So here to here means z is ranging from here 0 to this curve. This curve means z equal to 1 minus x square. So I can write this as integral z is varying from 0 to 1 minus x square z dz. So only this much I have taken. Next I want to put the limit for y. From where to where y is changing? Y is changing from here, right? So y is changing from here. When you are taking this projection of this t to xy plane, you can see that this y is ranging from here to here. So y is ranging from 0 to x. So y is changing from 0 to x. So we have considered the integral up to here also. Now we want to take what is x. X is ranging from where to where? Along this x-axis 0 to 1. So limit of x is 0 to 1. So altogether this integral will become integral 0 to 1 integral 0 to x 1 by 2 z square. Already done the integration for z square, right? Then z is from 0 to 1 minus x square. Again doing the same thing, we will get the answer as 1 by 12. Okay, now we can move to this y symbol region. Also I have given, we have explained this too at the beginning itself, so just you can read it. So example 3, evaluate integral over t square root of x square plus z square dv where t is the region bounded by the cylinder x square plus z square equal to 1 and the planes x plus z equal to 2 and y equal to 0. Y equal to 0 means nothing but the x-axis. Then y plus z equal to 2 means it's coming like this. See, the solid tree is viewed as a being by y symbol. So it's given like this. and its cross section when you are taking to this z plane, xz plane, it should be a circle like this. Now how to calculate this one? So integral over t square root of x square plus z square dv equal to integral over the rectangle. Then I should find what is the limit for y, right? So integral k1 xz to k2 xz square root of x square plus z square dy into dA. So this part is nothing but, see, only this much is coming as additional to us. Remaining is going to be the double integral, right? So this integral can be found out by taking the limit for z. Sorry, limit for y. So y is changing from here to this point, right? So here to here means this is 0. So 0 to y is ranging from this curve. What is this curve? 2 minus 8, right? So y is ranging from this to 2 minus 8. So y is ranging from 0 to 2 minus 8 square root of this into dy. Now for variation of r means, okay, you have found it out, this y, then we want to double integrate it. Now again for double integration we should consider this in the zx plane. Now in the zx plane you will get something like a circle, right? And this here you can easily see that when you are taking in this version, you will get your z is varying from where to where? Z is varying from this point to this, right? Or you can take from here also. So here's given. We can simply calculate this by converting everything into polar coordinates, right? So when you are taking here, the problem is that when you are taking as such, you have to find your z from this point to this point up to here, and x from -1 to 1. For x no problem, but here y may create some problem. So here the simple way is that we can convert everything into polar coordinates. So converting this into polar coordinates, we will get, see what is coming here. R is a circular region. It is more convenient to use polar coordinates when integrating. So here is only x and z is there, right? So you can put x equal to r cos theta, and y equal to, sorry, not y, z equal to r sin theta, and what is coming? Nothing else is there, right? So your dr, r dr should be equal to dx dy. So just we want to substitute it here. See, we have substituted everything here. So then integrating, your theta is running from 0 to 2 pi because it is the entire circle, and your r value is running from where to where? R is running from this point to this point, right? So 0 to 1. So integrating, simple integration only, we will get this as 4 pi by 3. Right? First we have integrated with respect to r, right? So integration we result like this. Next we are applying the limit r equal to 0 to r equal to 1. Next we are integrating with respect to theta, and we have got the limit as 4 pi by 3. Okay, I am stopping this session here. Thank you for your patient listening. Thank you.